In the video Introduction to Electricity, we defined voltage, current, resistance, and power. Now we can synthesize all of this to discuss electric circuits. These make use of wires, batteries, resistors, ammeters to measure current, and voltmeters to measure voltage to enable the transfer of electric energy. To truly understand circuits, we first need to define a concept called the electromotive force, or more commonly EMF, denoted by epsilon. Any circuit will contain a cell, a device that converts stored chemical energy into electrical energy in order to produce a current. Alternatively, it will contain a battery, a device which consists of multiple cells. The chemicals inside the cell create both a potential difference and an internal resistance. Due to the opposite charges, electrons flow from the negative terminal to the positive terminal. Current is taken to be in the opposite direction, so from the positive to the negative terminal. The work done in moving a charge from one terminal to the other is the electromotive force, equivalent to the work done divided by the charge. This unit, as we know, is equivalent to the volt. To continue our discussion on circuits, we must differentiate between two scenarios: parallel connections and series connections. If resistors are connected in series, we find the voltages of the resistors add up to the EMF of the source. Additionally, the total resistance is the sum of the resistances in each resistor. We can apply this to an example. For a circuit with an EMF of 5 volts and 3 resistors connected in series of 2 ohms, 3 ohms, and 5 ohms, what is the current? We can replace the resistors in series by a single equivalent resistance of sigma R, ergo 10 ohms. Then we use Ohm's law to solve for current. I equals V over R, so I equals 0.5 amps. What if we had 3 resistors in a parallel connection? This would imply that the initial current I splits into 3 currents for each path. By conservation of charge, this must equal the current leaving the 3 paths, leaving us to the result that the total current for resistors in series is the sum of the current in each path. Additionally, by Ohm's law, the current at each junction must be equivalent to the voltage divided by the resistance at that point. Then, the sum of these quotients gives the total current. Simplifying, we see this. We also know that the voltage divided by the total resistance gives the current. Hence, we obtain the result that the total resistance in a parallel circuit is the inverse of the sum of the inverses of the resistances at each junction. Now, we can combine this information to investigate circuits with both series and parallel connections. For example, what is the total resistance in this circuit? Well, all of these resistors can be simplified into one. On the top, we have a series connection. Hence, the total resistance here is 8 ohms. Now we have a parallel connection of one 8 ohm resistor and one 2 ohm resistor. The total resistance then is 1/8 plus 1/2, which is 5 over 8. Then we take the inverse of this, so the answer is 8 over 5 ohms. With all of these tools now, you should be able to handle most circuit problems. However, these can get complicated, and as such, it is highly important to consider each component individually. I'll go through some practice problems now, before we move on to some more content for circuits. The first problem involves the circuit shown. We need to first calculate the total resistance. Then, we want to calculate the power dissipated in the 6 ohm resistor. Give this problem a try before looking at my solution. First, we find the total resistance, which is done by attempting to merge all of these resistors into one. The initial parallel pair simplifies to 3 over 12, so we end up with 4 ohms. Then we add the series connection to get 8 ohms. All of this is parallel to the 20 ohm resistor, so we add the reciprocals and end up with 40 over 7 ohms. Now, to find the power, we need the current and the voltage. The top branch of resistance 8 ohms is connected directly across the terminals of the battery, so it gets the full 24 volts. Hence, the current here is 3 amps. For the individual resistances, the initial parallel pair had resistance 4 ohms, which leads to a voltage 12 volts. Since the 6 ohm resistor is in parallel, it experiences the full 12 volt drop. Since P equals V squared over R, we end up with a power of 24 watts. To move on, we can discuss how we measure these in practical setups. To measure current, we use an ammeter, which is connected in series. In order to allow the full flow of current, an ideal ammeter has zero resistance. To measure potential difference, we use a voltmeter, which is connected in parallel. An ideal voltmeter has infinite resistance so that it takes no current. If we connected a voltmeter across the ends of a battery, what would it read? This is a very interesting question, as we have previously assumed that the batteries are ideal, ergo they have zero internal resistance. In reality, however, there is, which will result in potential difference IR across the battery. Hence, the EMF decreases from epsilon to epsilon minus IR, which is what the voltmeter would read. To conclude our video, let's look at a final problem that combines every concept we've covered so far. Consider the circuit shown, where the real battery has an internal resistance of 1 ohm and EMF 12 volts. Note that the ammeter and voltmeter are both ideal. We want to find three things: the reading on the ammeter, the reading on the voltmeter, and the power dissipated by the internal resistance. Give this a try before looking at the solution. Just like before, we simplify the circuit from the inside out. The parallel pair of 6 ohm and 3 ohms simplifies to 2 ohms. We add this to a 3 ohm series resistor. So the total external resistance of the circuit is 5 ohms. But we must remember to consider the battery's internal resistance as well, which, for our calculations, functions just like a regular resistor. Adding that 1 ohm gives us a total circuit resistance of 6 ohms. To find the ammeter reading, which measures the total current, we use Ohm's law for the whole circuit. That's 12 over 6, which gives us exactly 2 amps. Next, the voltmeter. Remember, the voltmeter measures the terminal potential difference, which is the EMF minus the lost volts. The lost volts are IR, or 2 volts. Therefore, the voltmeter reads 12 minus 2, so 10 volts. Finally, the power dissipated by the internal resistance, which is, in this case, the energy lost as heat inside the battery. Using P equals I squared R, we end up with 4 watts. Thanks for watching, and have a good day.